myself, Dr. Surya Prakash. I'm working as assistant professor in the Department of PCB at NITC Calicut. So this institute, this is present in Kerala state of India. So I'm presenting this talk as part of fourth international conference on applied control, electrical and electronics engineering that is being held at Dubai. So the title of my talk is Distributed Arithmetic Based Signed-Regressor LMS Adaptive Filter. So this LMS, the full form of this is least means mean, which is a well-known algorithm that is used in adaptive filters. So adaptive filter, we already know that it has wide range of applications. This is mainly used in noise cancellation, and then system identification and channel equalization. So this talk is mainly about implementation of this Signed-Regressor LMS adaptive filter using the design aspect called distributed arithmetic. So this Signed-Regressor LMS, this is just a variant of the least mean square algorithm. And here are the contents of the presentation. I'll give a brief introduction on what is meant by distributed arithmetic. And then there are some variants of distributed arithmetic that also will be presented. And a brief description about an adaptive filter, which works based on an adaptive algorithm. And here the discussion will be based on least mean square algorithm and Signed-Regressor LMS algorithm. And finally, we'll talk about the implementation of this least mean square adaptive filter using distributed arithmetic. In fact, if we are able to understand how we are able to implement distributed arithmetic using least mean square algorithm, the same can be extended to even this Signed-Regressor LMS algorithm. So that's the reason this talk focuses upon implementation of LMS adaptive filter using distributed arithmetic. Next, results will be presented, and we are going to talk about future working. So distributed arithmetic, basically this is a bit level architecture for computing the dot product or inner product of two vectors C and X, consisting of elements Ci and Xi. So this is the equation of the inner product of these two vectors, and assuming the length of the vectors to be capital N, sigma I ranging from 0 to n minus 1 Ci dot Xi. This is what is the inner product of vectors C and X. Now, if you are able to represent the elements of vector X, which we are calling as Xi I ranging from 0 to n minus 1, if you are able to write the binary representation of Xi, it will take this kind of a form. Xi is equal to sigma j equal to 0 to b minus 1 bij and 2 power j. So j here is the index for bit position. Clearly we can see that we have used a total of capital B number of bits in order to represent Xi in binary form. Now, if you are able to substitute this equation in the inner product equation, this is the form it takes. If you are able to just rearrange the summations in this particular order, we arrive at this particular equation. So clearly we can see here the first summation, j is equal to 0 to b minus 1. Here j is the index for the bit position, and I is in fact the index for the element in each of the vectors. So a total of n elements are present in each vector, and each element is being represented in capital B number of bits. So clearly we can see here, if you are able to store the terms that is present inside the bracket, just by shift and add operations, we'll be able to compute the dot product. That's because anything multiplied with 2 power j, that's what is a shift operation. If j is negative, this will be a left shift operation, and if j is positive, that will be a right shift operation. So clearly we can see from this expression that just by using shift and addition operations, we will be able to compute the dot product. So that's the reason we say distributed arithmetic. This basically avoids the usage of hardware multipliers. Generally, researchers tend to avoid usage of hardware multipliers because multipliers take good amount of power consumption. They also lead to good amount of propagation delay. So this is the basic idea behind distributed arithmetic. We are in fact computing the dot product just by shift and add operations. In the process, we are eliminating the usage of hardware multiplier. And that's in fact can lead to savings in terms of power consumption, also in terms of area consumption. So earlier we have considered representation of xi in binary form. So xi can be a negative number too, and in that case we can go for signed-2's complement representation. And the first equation, that is the signed-2's complement representation of xi. So in that case, the final dot product expression that will be reduced in this manner. So here we have the first term taking a negative sign, and the next term that is same as that of previous equation. So from this particular equation, we will be able to derive the architecture for it. So the rightmost part, that's what shows the shift and accumulate operation, and whatever we have inside the brackets here, because bi, b minus 1 minus j, that's what is a binary bit. It takes either 0 or 1 value. Even here in the first square bracket, we have bi comma b minus 1. This also is a binary bit. So this also takes a value of either 0 or 1. And because this is summation of ci into bi, b minus 1 minus j, a total of 2 power n combinations are possible. Assuming capital N to be equal to 4, a total of 16 combinations are possible. So we are simply storing all these possible combinations in memory, and we call all these combinations as partial products. So in this particular, for deriving this particular architecture, we were assuming capital N to be equal to 4, and clearly we can see we have a total of 16 combinations. And in fact, if all bi, b minus 1 minus j's are zeros, the inside term will be 0. And if only one particular bi comma b minus 1 minus j is 1, we'll have that corresponding ci value. So that's what we can see here. In the first address location, we have all bi's taking zeros. That's the reason we have in the first location 0 value stored in the lookup table. And then in the next address location, the address bits are 0, 0, 0, 1. And in that particular case, only one particular ci has been taken, and that's what is stored in the first address location. Similarly, in the next address location, we see 0, 0, 1, 0, only C2. In the same manner, we can see in the final location, we have all address bits taking once. So that's the reason we have all CIs available in the last address location. So here, what's finally happening is that for computing the dot product between two vectors, we are accessing one particular address location, and then we are using appropriate amount of shift upon that particular value, and then we are adding to the shifted version of the next value. And through a series of shift and add operations, we are able to compute the dot product. So clearly you can see here this basic DA processing unit. This is completely avoiding the usage of hardware multiplier. It only takes a lookup table, which is a memory, and then we have only shift and add operations. And in fact, in order to store the binary bits of x's, we have registers available. So clearly this completely eliminates the usage of hardware multiplier, and that's the reason researchers have tendency to choose this particular architecture when they are going for hardware implementation. So for computing the dot product of two vectors of size capital N, we need a memory of size 2 power n. And then assuming capital B number of bits are used for representing each xi, the dot product can be computed in exactly B number of clock cycles. So these are the highlights of the basic DA processing unit. So we have some variants in this distributed arithmetic architecture. In fact, whatever is presented earlier, that says or that concludes that given 2 vectors of length capital N, we need a memory of size 2 power n. And if we are going for very large length vectors, let's say the length of the vector is 256. In that case, we need a very huge memory requirement, which is 2 power 256. And such large sized memories are difficult to obtain. And for this reason, we have one variant of distributed arithmetic called as ROM decomposition variant. In this case, instead of going for a very large sized memory, we can use multiple small sized memories. That's what is one variant of distributed arithmetic. And then the basic DA processing unit, it takes B number of clock cycles for computing the dot product of 2 vectors. But if at all we have to get the dot product computed in a comparatively less number of clock cycles, we have one more variant, and that's what is digit serial scheme of DA. So this is a ROM decomposition variant. This is based on splitting this particular n in terms of m and k. So here we will use m small sized memories, and the size of each memory is 2 power k. And this also takes a total of b number of clock cycles for computing the dot product of 2 vectors, just like the basic DA processing unit. So the same dot product of 2 vectors of length 4. Earlier we were using a single memory of size 2 power 4, but here we are using ROM decomposition technique, and that's the reason we can clearly see we are using here 2 small sized memories, and the size of each memory is 2 power 2. So this is what is the ROM decomposition variant. The next variant of distributed arithmetic, this is what is digit serial scheme variant of distributed arithmetic. While the ROM decomposition technique, that is based on splitting capital N into M and K, this is based on splitting B in terms of P and Q. So here the memory size requirement will be 2 power P into N, and the advantage of this particular scheme is we will be able to compute the dot product in a comparatively less number of cycles, and that is in B by P number of clock cycles. So the original DA processing unit that takes a total of capital B number of clock cycles, but this takes B by P number of clock cycles. So that's the reason if we want the dot product to be computed in a less amount of time, we can go for digit serial scheme of distributed arithmetic. So the same dot product of 2 vectors of length capital 4. Here we can see the combinations are differing from the basic DA processing unit. So this is what is the architecture for digit serial scheme DA, which is used for computation of dot product of vectors. And in digital signal processing, basically almost all DSP operations, they are inner product operations. We go for the convolution operation, correlation operation, all the transforms, whether it is Fourier transform or discrete cosine transform. All these are basically the sum of product operations or dot product operations. That's the reason earlier researchers they have focused upon implementing all these algorithms using distributed arithmetic. So basically in DSP we have finite impulse response filter, infinite impulse response filter. So the output of these 2 filters, they are basically the dot product of input vector and then weight vector. So these have already been implemented using distributed arithmetic. And then we find even the rotation operations in digital signal processing, these are also implemented, and adaptive digital filters. In fact, adaptive digital filter is basically a digital filter whose weights are updated from time to time. So these are also implemented using distributed arithmetic. And in the process of implementation, some approximations were made to the standard weight update algorithms. And that's the reason some of them are impractical to implement. Next, even in the recent past, we have observed implementation of adaptive filter algorithms using distributed arithmetic. And some were focusing on the other algorithms like block LMS, delayed LMS, and some have used techniques like pipelining, parallel processing. And then one of the works that is reported in the recent past, that's a non-optimal weight update scheme. So that's the reason we were going for optimizing the implementation of adaptive filter algorithm using distributed arithmetic. So this diagram shows the implementation of a finite impulse response digital filter using distributed arithmetic. The output of a finite impulse response digital filter, that's what is the convolution between the weight vector and input sample vector of the filter. So which is nothing but a dot product operation. So that's the reason implementation of a finite impulse response filter using distributed arithmetic that is quite easy. So here we can clearly see the partial products are the partial products of the filter weight vector. Earlier in the example of DA processing unit, what we are seeing is the partial products of C vector. So here what we see are the partial products of input weight vector. And in the registers are stored, these registers are storing the different input samples, and just by shift and accumulate operation, we will be able to obtain the output of a fair filter. So there is one more variant of distributed arithmetic called offset binary coding scheme, and this is based on this kind of a replacement. Xi is equal to 1 by 2 Xi minus of minus Xi, and the advantage of going for this kind of distributed arithmetic variant is that the memory size requirement will be reduced by a factor of 2. The basic DA processing unit that requires a memory of size 2 power n, and this in fact requires a memory of size 2 power n divided by 2. And this also takes exactly b number of clock cycles. And here is the OBC based distributed arithmetic implementation of a finite impulse response filter. Clearly we can see here the partial products are taking some complex combinations compared to the original DA processing unit. So next, a short introduction related to adaptive filter. So basically an adaptive filter is an unfair filter whose weights are updated from time to time. And here we have different types of algorithms, adaptive algorithms, out of which LMS being the most popular one, least mean square algorithm. And we have some variants of least mean square algorithm like signed LMS, Signed-Regressor LMS, and we have other adaptive algorithms too, like delayed LMS and recursive least squares algorithm. So the basic idea behind the operation of this adaptive filter is that first the inputs are provided to the FR filter. From that we obtain the output, which we call as Y of n. There is something called as desired sequence D of n. Error will be computed by taking the subtraction of these two, and that error will be fed to the least mean square algorithm, and that algorithm is used for updating the filter weights. So this is the basic idea behind the operation of the adaptive filter. And earlier we have already seen the implementation of FR filter using distributed arithmetic. We have simply stored the partial products of weight vector in the memory, but because an adaptive filter actually in this the weights are updated from time to time, we need to update the partial products from time to time. That's what is the challenge involved while we are going for implementation of adaptive filter using distributed arithmetic. So the basic operation summarized in terms of equations. First, we have the filtering equation Y of n. That's what is the output of the adaptive filter. We can clearly see that it's this is the dot product of two vectors, and then error computation, which is nothing but the difference between desired signal and the output of the FR filter. Next, we have weight update recursion, W new, which is the vector taking new set of weights that is updated based on old weights plus mu into E of n into x. So this is what is the equation related to LMS algorithm. Signed-Regressor LMS, this is nothing but the variant of LMS algorithm. So the equation is similar, except that for updating the weights, we are taking the signum of x in this particular case. So the traditional way of implementing an FR filter is basically the usage of multiply-accumulate units, which we in short call as MAC units. So in fact, the same MAC units are used for the implementation of adaptive filter. So this is what is implementation of FR filter using distributed arithmetic. And in fact, this is what is using the OBC scheme. So the main challenge involved now for the implementation of adaptive filter is to update all these partial products from time to time. So this is a very basic idea where we are implementing the adaptive filter using distributed arithmetic. Instead of going for a lookup table, what we are using is we are simply storing all the partial products, all the filter weights in registers, and just by using AND gate and add a tree structure, we are able to compute all the partial products. So this kind of a structure gives us chance to update all the filter weights because each of the samples of input samples are stored in separate registers. We will be able to easily update all the filter weights. So this is the initial idea we came up with, and this kind of idea was published in a conference held at Singapore. And one of the ideas that is existing in literature is what is presented here. We have the first lookup table here, which stores the partial products of filter weights. The other lookup table, this is what is auxiliary lookup table. This stores the partial products of input samples. So just by multiplying one of the values available in this DA auxiliary lookup table with mu into E of n, if we are able to add that value to the corresponding address location value of DA lookup table, and if you are able to perform this for all address locations, the weight update operation will be complete for that particular iteration. So based on this idea, we have come up with one particular architecture that is similar to the architecture that is presented now. Earlier the researchers in that particular architecture, researchers were calling with the name DALUT. Here we are calling this as primary lookup table. They were calling the other lookup table as auxiliary lookup table, and we are calling this as secondary lookup table. All the remaining elements will be the same, the register bank and then shifted accumulator block. And in fact, we have introduced one more thing here called R0 register, the purpose of which will be explained later. So this primary lookup table, this stores the combinations of all the weights, and secondary lookup table, this stores the combinations of the recent input samples, except that of the most recent input sample, and that's what is stored in register R0. So here are the contents of primary lookup table and secondary lookup table during the time instant n. Here we see OBC combinations of filter weights and similar OBC combinations of input samples in the secondary lookup table. So the weight, these equations are that of the primary lookup table partial products and secondary lookup table partial products. It's just that these partial products are expressed in terms of mathematical equations. So these are basic LMS filter equations. In iteration 1, we can see the updated weight update operations are summarized in this manner. W0 is the weight that requires sample x of n. W1 is the weight that requires sample x of n minus 1. Similarly, W3 is the weight that requires sample x of n minus 3 in iteration 1. And if you are going for the next iteration, W0 requires x of n plus 1, W1 requires x of n, so on. W3 requires x of n minus 2. So from these two, we can clearly conclude that while we are moving to the next iteration, the oldest input sample that is required in the previous iteration is being eliminated. And that's what we can see from this figure, isn't it? So iteration 2, in this, the oldest input sample is x of n minus 2. And if you are going for iteration 3, the oldest input sample is x of n minus 1. So whatever is the oldest input sample in iteration 2, x of n minus 2, that is not useful for weight update operation in next iteration, which is iteration 3. So this actually shows that in every iteration we have a necessity to eliminate the oldest input sample. So based on this idea, we have come up with a secondary lookup table update scheme. Basically, the zeros and ones we see here are not the actual zeros and ones, but they represent the sign of whatever is the term present above. For example, if you consider the left table, we have on the top x of n minus 1, x of n minus 2, and x of n minus 3 samples. So in the first location, we have all zeros. This simply represent in the first location, we have the term minus 1 by 2 into x of n minus 1 minus x of n minus 2 minus x of n minus 3. And in the second location, we have 0, 0, 1. This represents minus x of n minus 1 minus x of n minus 2 and plus x of n minus 3. So in short, 0 here represents negative sign to that of the term that is present above it, and 1 represents the positive sign to the term that is present above. And because we have a necessity to eliminate the oldest input sample, when we are moving from iteration n to iteration n plus 1, we have the necessity to eliminate x of n minus 3 term, which is the oldest input sample in the nth iteration. So that's the reason if we are able to sum the values of 2 consecutive address locations, we will be able to eliminate the oldest input sample, which is x of n minus 3. Because the sign of this oldest input sample, x of n minus 3, is alternating between different address locations. So 0, 1, 0, 1, 0, 1, 0, 1, this is how it goes. So that's the reason if you are able to add the values of 2 consecutive address locations, because we have alternate signs there, the oldest input sample will be eliminated. This is what is the novelty involved in our work. And because we have also the necessity to accommodate the newest input sample available in the next iteration, we are taking the help of R0 register. And here in the nth iteration, we can clearly see that the partial products are taking, the signs of partial products are taking a binary pattern, starting from all zeros to all ones. Even in n plus 1 iteration, we have such a necessity, but because of this particular secondary lookup table update scheme, what we are ending up with is not a binary pattern, but a circularly right-shifted version of the binary pattern. So on the left-hand side, we can see the binary pattern. In the first location, 0, 0, 0, 0, 0, 1. But in the second table, we see 0, 0, and 1, 0, 0, which is nothing but the circularly right-shifted version of whatever is available in the left table. Similarly, on the left-hand side, we have in the second location 0, 1, 0. In the same second location, in the right-hand side table, we have 0, 0, 1, which is nothing but the circularly right-shifted version of whatever is available in the second location of the left table. So in the same way, all the values, whatever they are available in the left table, they are nothing but circularly right-shifted, and they are placed in the right-hand table. So based on this observation, we can conclude that just by left shifting the address bits, we can access the secondary lookup table in the next iteration. So that's how we counter the presence of circularly right-shifted version of the binary pattern, presence of binary pattern in the secondary lookup table. So in the nth iteration, we'll have binary pattern. In the next iteration, we'll have a circularly right-shifted version of it. And in the next iteration, it will be the circularly right-shifted version of whatever is available in the previous iteration. And so for a 4-tap filter, once again, we arrive at the binary pattern in the n plus 3rd iteration. So the secondary lookup table weight updates, secondary lookup table update scheme, that's what is summarized in terms of equation here. And we have summarized the operation of this particular adaptive filter in terms of an algorithm. The first one, y of n, that's what is the computing the output of FR filter. The second one, SA open. So this equation is related to secondary lookup table update scheme, and we have error computation, and then whatever is the equation available in the fifth step, that's what is the weight update equation. So coming to the results, what we see is the throughput of this particular filter is almost constant and doesn't vary with respect to filter order. So what we have done is we have computed the throughput in terms of number of clock cycles the system takes for computing one sample of the output. And this is what is based on these parameters, capital B, K, and small m. So these are the convergence curves. The first one is that of distributed arithmetic based implementation. And the second one, this is based on the traditional multiply-accumulate based implementation. Clearly, we can see there is no much difference in terms of convergence performance. So this is the area comparison chart. On y-axis, we can see the area in millimeter square. On the x-axis, we see number of filter coefficients, eight coefficients in the first case, 16, so on up to 128. And whatever we see as shaded rectangles here, they are that of the existing implementations. And whatever is available as unshaded rectangle here, that is that of our proposed implementation. Clearly, we can see in all the cases, our proposed architecture is consuming less chip area. And this is what is the throughput plot. On y-axis, we have throughput in terms of number of samples processed per second. On x-axis, just like the previous case, we have number of filter coefficients. Whatever we see as inclined lines here, majority of them are related to existing implementations. And whatever we see as horizontal lines, they are that of our proposed implementation. So the conclusion that we can derive from this figure is that not only the throughput is all these horizontal lines, they are staying above these inclined lines, which means that our proposed system has a better throughput. They are remaining horizontal for the entire duration of this x-axis parameter, which simply shows that the throughput is almost constant with respect to filter order. Or in other words, the throughput is not changing with respect to filter order. And that's the reason this proposed implementation is suitable for even for higher particularly with the ones that are published recently. So the throughput and then adders, registers, the count of them for different implementations. So we have different schemes available on the left-hand side. All these are works that are published recently. And the final row is that of our proposed implementation. So the throughput equation and then number of adders, number of registers. And after implementation, our summary is that our proposed implementation, this is able to take 87% less number of adder units compared to the existing implementation. And because this is using distributed arithmetic scheme, it is basically a multiplier-less implementation. So that's the reason it is completely avoiding the usage of hardware multipliers. And there is almost 25% reduction in chip area. And then if you have to talk in terms of throughput, the throughput is 2 times more than the best existing architecture and almost constant with respect to filter order. So our future work focuses on implementation of other adaptive algorithms like delayed least square algorithm and then recursive least square algorithm. So there is some scope for the implementation of these 2 algorithms. And in fact, even if we have to talk about the same implementation, which is Signed-Regressor LMS based implementation, because the weight update algorithm that is based on signum value of x, there is some scope for completely avoiding the usage of auxiliary lookup table. So if you are able to eliminate the usage of this auxiliary lookup table, there is some chance of reduction in chip area. So that's the reason our future work focuses on implementation of these two. So these are all the references. Thank you.